First, we let G be a multiplicative routine group, and let Fg be the binary semigroup with basis G. Since G and Fg both have appendices, we use a dot to denote the multiplication in G, and we use a bold dot to denote the multiplication in Fg. And we call the elements of Fg sequences over G. Thus, a sequence over G, we mean an unordered finite sequence with terms from G, and repetition is not. The operation of Fg is just the concatenation of sequences, and the identity element of Fg is just the empty sequence. When let S be a sequence over G, we can reach in the G1 up to GL, which concatenated by the bold dot. We define the set of products of S, which is the set of those elements. We give, since S is unordered sequence, we give it order to the terms such that there is a product. So for every order, there's a product of the terms, and pi S is the set of all the product. We say example, we let D2N be a dihedral group. Then we let W is a sequence with 4 terms, X, X, Y, X, and Y. Since W is unordered, we can still written like this, X to the power 2, X, Y, and Y. Here we use a bracket to denote the exponentiation in Fg. Then the set of pi W is such a set with element X, X, Y to the power 2, X, Y to the power -2. Here the X, we just see this order, X, X, Y, X, Y, then the product is X. And see this order, X, 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 Y, and Y, then the product is X, Y to the power 2. We go through all the orders of the terms, we get the set of pi W. We say S is a subsequence of T if S divides T in Fg. That means that S is a subsequence of T, and the terms of S is chosen from T. We say S is a product 1 sequence if this 1G is in pi S, which means that there is a order such that the product of the terms of S equals 1. We say S is product 1 free if every non-empty subsequence of S is not a product 1 sequence. We say S is minimal product 1 sequence. If S is a product 1 sequence, and S cannot be written as a product of 2 non-empty product 1 sequences. Which means if S can be written as a product like U and V, then U or V must be empty. We see an example. We still record this W. The W is a sequence over D2N. Then we choose the term X, X, Y, and Y. This U is a subsequence of W. And this U with the order X, Y, X, Y, the product is 1. So this U is a product 1 sequence. And it's not difficult to see U is still a minimal product 1 sequence. We consider another sequence with the term X, choose a term X, Y, and Y. We have 2 terms. It's easy to see that this way is a product 1 free sequence and it's a subsequence of W. Now we consider the set of all product 1 sequences over G. Still, since 2 product 1 sequences, their concatenation is still a product 1 sequence. So this BG is a sub-semigroup of Fg. Now we give the definition of Dumbbell constant. We define the small dg is a small Dumbbell constant, which is a sup of the length of S. S is a product 1 free of all product 1 free sequences, and the large Dumbbell constant to be the sup of all the length of all minimal product 1 sequences over G. It's easy to say if G is an infinite group, then the Dumbbell constant small Dumbbell constant and large Dumbbell constant are infinite. So we suppose G is finite. Then we have this inequality. This small Dumbbell constant plus 1 is smaller or equal to the large Dumbbell constant. This can be seen that for we choose a product 1 free sequence. We want to add another term such that the new sequence is a product 1 sequence. So we choose one element G from the set of product. Then we add the new element, the inverse of G, to S. So the new sequence is a product 1 sequence. And it's easy to see that this is a minimal product 1 sequence. If G is a linear, and we can see that the equality holds, this can be seen if we have a minimal product 1 sequence. So we take one element out, then the remaining sequence is a product 1 free sequence. But this can only hold if G is a linear. If G is not linear, with the following example, still for dihedral groups, we choose S be such a sequence. Each term X and Y appeared twice. So S is a minimal product 1 sequence, but we take the term Y out. So the remaining sequence is not a product 1 free sequence. Since the X to the power 2, this sequence is a product 1 sequence, and it's a product 1 subsequence of the remaining sequence. Okay, we see more on the Dumbbell constant. If G is a finite abelian group, then G can be written as a direct product of cyclic groups. We can demand that N1 divide N2 to divide NR. Then this diety is denoted by this 1 plus the sum of Ni minus 1, which is the lower bound of DG. The classical result shows that the equality holds for P groups and rank 2 groups. Many mathematicians worked on it, but there are only very limited progress. Our conjecture is that the equality holds for rank 3 groups and for groups G, which is isomorphic to our copy of the cyclic group. In 2012, Lieberman, Gordinger, and Philip, they found a group that G is isomorphic to this C2, has our copy of 2n, where n is word. For this group, they found that the inequality holds for where r is larger than or equal to 4. So our conjecture, and just few examples show that if the rank is larger than or equal to 4, then there's an infinite many groups such that the inequality holds. Okay, we consider abelian groups. Now we consider general groups, especially here is about the non-abelian groups. When let G be a finite group, Gordinger, Grinkovich, they proved that if G has a cyclic subgroup with index 2, then the large Dumbbell constant equals the little Dumbbell constant plus the order of the commutator subgroup of G. In particular, if G is a dihedral group, then we know the exact value of the large Dumbbell constant. If n is odd, then the large Dumbbell constant of D2n equals 2n, which is just the order of the group. If n is even, then the large Dumbbell constant equals 3/2. The same year, Grinkovich also proved if G is neither cyclic nor a dihedral group of order 2n with n is odd, then the large Dumbbell constant of G is smaller or equal to 3 times the order of G over 4. So by those two results, we obtained that if the large Dumbbell constant dg equals the order of G, if and only if G is either cyclic or G is isomorphic to a dihedral group of order 2n with n's odd. Here is a remark that if we know that if G is a linear group, then only proper subgroups, the Dumbbell constant of the only proper subgroup is strictly smaller than the Dumbbell constant of G. But if G is non-linear, there exists a proper subgroup H. such that the large Dumbbell constant of G equals the large Dumbbell constant of H. Okay, next we will talk about the omega invariant. First, we give the definition here. Let G be a general group, and let S be a product one sequence over G. We define the omega S to be the smallest integer T with the following property. If there exists, if there is a product is U1 up to UN, if S divides such a sequence, here in BG, which means that if we take the sequence S out from the sequence U1 up to UN, the remaining sequence is still product one sequence. Okay, if S divides such a product, then there exists a subproduct such that S divide such a subproduct in BG, and for this subproduct, that means the size should be bounded by this T. And we let this omega G to be the soup of all the omega S, where here we demand that S is a minimal product one sequence over G. Here we demand that S should be minimal. Otherwise, if S just a product one sequence, this sequence the length could be goes to infinite, then omega G should go to infinite. And this omega invariant is a classical arithmetic invariant in factorization theory, and which can be used to study state of distances, quaternary degrees, and time degrees. But I do not introduce definitions here, and I just do not want to give you the definition from algebra side, but just this invariant, and it's very important. So we go on to talk about this invariant. We see some examples first. We let G be a cyclic group of order 2. Then there are only 2 minimal product one sequences. First one is just the identity element 1. Next is just the E appeared twice. For both these sequences, the omega invariant equals 1. Omega 1 equals 1. This is obviously. But for the next one, if this can see easily send itself for only product one sequence over G, if E appeared, if E is a term of that product one sequence, E should appear at least twice. I mean, it's even times. So you can see that the omega invariant of E power 2 is 1. Once we know the omega invariant of G equals 1, which is strictly smaller than the Dumbbell constant. Okay. Next, we see in another example. Now, next we also consider the non-binary groups. Now, our candidate is the dihedral group. We choose S, U1, U2, and U3. We check it. We see this both these 4 sequences. These are product one sequences. Here we demanded that N is not enough. Then we know that S should divide this U1, U2, and U3 appear twice in B, D2N. Since if we take the S out from the sequence U1, U2, and U3 appear twice, the remaining sequence is a product one sequence. You just do a simple calculation. But we know that S do not divide this U1, U2, U3. Since we consider S should divide a subproduct, and S has element at terms x, xy to the power 3, and y to the power 3, so we must have this U1 and U2. So if we have another one, we should have this U3, but S does not divide U1, U2, U3. Since the remaining sequence is just xy to the power 6 and x with U3, this is not product one sequence. So we obtain the omega invariant of S is larger than or equal to 4, which is strictly larger than the length of S. Okay, next we consider if G is a binary group, if G is a finite binary group with, here we demand that the order is larger than or equal to 3. If the order of G is 2, we know that the omega invariant is 1, which is strictly smaller than the Dumbbell constant. But here, if the order of the group is larger than or equal to 3, we obtain that the omega invariant of G equals the Dumbbell constant of G. Here we show this by we show that for every minimal product one sequence over G with the length is larger than or equal to 3, we obtain the omega invariant of S equals the length of S. The proof is simple, and we can see a fact first. If UV are both product one sequences over G, and U is a subsequence of V. U is a subsequence of V, which means U divide V in Fg. Then we can see, since G is a Banner group, the set of product has only one element. Since the order of the product don't influence the product, so U also divides V in this Bg, which means that the remaining sequence we take U out from. V is a product one sequence. We can see since the set of product of U times the set of product of the remaining sequence contained in the set of product of U, and the set of product U had only one element, and just the identity element, so this remaining sequence is the product one sequence. Now we consider S divide such a product U1 up to UT. We want, since here S divide this product, here is equivalent to consider dividing Fg or Bg. So we want to find a subproduct. So we want to choose the terms. Every term from S is chosen from these UIs. So we can choose a subproduct, then the size is bounded by the length of S. Since S has most length of S terms, so the omega S is bounded by the length of S. On the other hand, we suppose S equals its G1 up to GL, and let this UI be the sequence is GI and the inverse of GI. So this UI are product one sequences. So S divide the product U1 up to UL. But S does not divide any proper subproduct. Since if S divides any subproduct, since the length of S is L, so there must some UI should be a subsequence of S. But the length of S is larger than 3, we get a contradiction. Okay. Now here is our main result. In last year, Gordinger, Grinkiewicz, all we together, we prove that if G is a dihedral group of order 2n with n word, then the omega invariant of G equals the night Dumbbell constant of G equals the order of G. Here we consider the dihedral group of order 2 with n is odd. We do not consider about n is even, since we see that if the Dumbbell constant of G equals the order of G if and only if G is cyclic or G is isomorphic to a dihedral group of order 2n with n word. So if n is even or odd, they are very different. And to show this, we need to know some structure, right? Which means the following proposition: if G is a dihedral group, order 2n with n is odd, and for only minimal product one sequences, we know the structure of the sequence. I mean, the maximal minimal product one sequence of length dg, which means that there exists base generality set xy such that S should be that y appeared 2n minus 2 times and x appeared 2 times, or S equals such a, it means the term x and xy both appeared n times. Now we choose such a sequence S, which means x and xy appeared n times. Since the sequence S times S, because this sequence can be refactorized as a such term x to the power 2 appeared n times, and xy to the power 2 appeared n times. So this is a product of 2n product 1 sequences. So S divides such a product, but S does not divide only proper subproduct. This shows that the omega invariant of G is larger than or equal to the omega invariant of S, which is larger than or equal to 2n. On the other hand, we want to show that the omega invariant is smaller or equal to 2n. This is to do that, we see a special case. First, we assume we choose this xy be a generating set. Then we consider this sequence x to the power 2. This is a minimal product 1 sequence. It's easy to say that the omega invariant should be larger than or equal to 2. It cannot be 1. We suppose this sequence x to the power 2. Let's divide this u1 up to ul in Bg. So x to the power 2 has only 2 terms. These 2 terms can appear in just one UI or appeared in 2 different UIs. So if there exists 2 index, we say 1 and 2, such that x is a term of both u1 and u2. Thus, we consider the remaining sequence. We take the term x out from u1 and take the term out from u2. Since the x has order 2, now the x is a product. Now x is in the set of product of the u1 times x takes x, the remaining sequence of u1 and the remaining sequence of u2. So the product, so we consider this sequence u1, u2, we take the sequence x to the power 2 out. So the remaining sequence, this is a product 1 sequence. And the other cases that means the 2 terms x appear just in one product 1 UI. We assume that x to the power 2, this is a subsequence of u1. Then u1 can be written in such a form: x times t1 times x times t2. Since u1 is a product 1 sequence, then this t1 and t2 and the set of products of t1, t2, the intersection is non-empty. If the sequence t1, t2 has a term from x times the subgroup generated by y, then t1, t2 is a product 1 sequence, product 1 subsequence. And hence, the sequence x to the power 2 divides u1 in Bg. If the t1, t2 has no term from x times the subgroup generated by y, then this u2 times up to ul has a term from x times the group generated by y. It's just because that here we know that the x to the power 2 divide u1 up to ul in Bg. So this u2 up to ul must have a term from x times the subgroup generated by y. We say u2 has a term from x times the subgroup generated by y. Then the sequence t1, t2, and u2 must be a product 1 sequence. Whence x to the power 2, this divide u1, u2 in Bg. Put all together, we obtain that the omega invariant of x to the power 2 is 2. Here, this is basically to show that we give a minimal product 1 sequence. We want to show that this is a very simple case. In fact, we cannot hope that give a minimal product 1 sequence. What about the omega invariant equals the length of the sequence? We see the example here, and we know that the omega invariant of the sequence could strictly larger than the length of the S. And to show this theorem, we need a generalized partition theory. And as the proof is very complicated, we did not give too much details, but we just show we will use this partition theory. And here we use additive notation again. And for here, finite binary group as a sequence over G, we want to study the sum sub NS, which is a set of all the sum of the sequences of length n to study such a set. If we have a set partition S prime, if S prime can, I mean, is A1 here, A1 and AN are all non-empty subsets of G, it immediately see that the subset of this AI is a subset of the sum sub NS prime, which is a subset of sum NS. So we can use the result from the sum set to study the subsum N. The following theorem is one version of partition theory. If you're interested, you can see it. But I always want to talk more about this because there's many partition theories. We use a generalized partition theory, which is more complicated than it. We just give the feeling that we will need many things to finish that proof, but the details is missing. But I hope that we let everybody to know exactly the problem questions. Thank you.
Thank you very much. We have a few minutes. Are there any questions for our speaker? If not, then I thank the speaker again for his talk. And our next talk will start in 4 minutes. Thank you.